Now we need to have some introduction on how to describe the spray characteristics. Before we go to these sections, this section we will start from the page 3.8. And before we go to study the spray characteristics, I need to mention last time I forgot the name for the funnel, Lodo. Actually, in that experiment, I used two funnel and I cut the neck of the furnace and then bring two furnace together, one inside, the other one is outside. Then you will have an open region between these two funnel surfaces. Okay, and I drill a small hole and on the surface, on the outer surface of the surface of outer funnel and connected a small tubing and allowing water moving from the tubing into the nano region between two furnaces, and then the water will flow into those regions and starting from the upper part, and they will follow gradually has a circulation, then impinging out of the final small holes on the bottom. And this kinds of structure basically can be used to describe the flow the sorting flow for the simplex nozzle. Then when you do the experiment, you try to increase the water velocities, then the sorting strength will be enhanced. Then you will produce a different kinds of spray breakup characteristics as we described earlier in the last slide in last time. Okay. Furnace. Okay, I'm sorry. I forgot the English name for the loader. Okay, now we go to the these sections to describe how to present the spray characteristics. Because when you apply a spray into different kinds of application, you will think about, is this spray good or that one is good? What is the physical characteristics are important? Okay, are important. Then we need to have some try to think about the main purpose for using the spray. Okay, but now I will give you some description on that. The first one we try to think about because we already introduced the jet breakup, a small tiny water jet then break up to the droplet, right? And we need to identify the breakup mechanism. And fortunately, this breakup process initiated by the instability of the excitation or perturbation from the surrounding or from the pressure or from the temperature as we described earlier. But those kinds of instability is predictable and was presented by radar predictions. Okay, now they give the radar give a very important conclusion is that a circular current of liquid become unstable. Now you have some excitation. Okay, they make there is the wave disturbance on the surface of the current of the liquid. Then they will break into droplet when the amplitude of a small turbulence. Okay, now we emphasize radar find out the amplitude of the disturbance. Then they were symmetrically acting on the axis of the jet and grow to 1/2 of the diameter of the undisturbed liquid jet. This is very important. The frequency, or we call the wavelength, is large enough and to match just the half of the diameter of the initial liquid jet. Then they will have enough intensity, enough strength to break the liquid current to become a droplet. Okay, this is the first one. You can see the strength of the amplitude of the disturbance is large enough, just equal to 1/2, then they will break the ligament into droplets. Okay, when you have this ligament, that means that this is just one wavelength of your liquid current. This occurs, the liquid length is equal to 4.5 dj. Dj means the jet diameter. Okay, at this moment, the amplitude is half of the diameter of the liquid jet, and the wavelength is 4.5. Actually, 4.5 is equal to pi times square root 2. Okay, and this is a 4.5. At these conditions, then you will find out the droplet will be formed spherical. Okay, here lambda is the wavelength of disturbance, and dj is the initial jet diameter. Then you can figure out under these conditions, you break a current of liquid, then you can calculate the total volume of the current, right? This is the cross section of your the liquid current, and lambda is the wavelength. You already cut it and try to form a droplet. The total volume will equal to a spherical droplet volume. That means the 1/6 times pi t cubits. Then you will find out by these definitions, the volume of your droplet equal to the volume of the liquid current. Then you can estimate the droplet size. The droplet size is equal to 1.89 dj. Okay, this is predicted by radii theory, and based on the instability of the by capillary effect. Okay, they say in the volume of the spherical drop is equal to the volume of a cylindrical ligament of the length equal to the wavelength, the length of the broken liquid current, and the diameter equal to the jet diameter. Then they can estimate you may have the droplet size equal to 1.89 diameter of the initial jet. Okay, this is the original prediction by the radii. Basically, they just consider when you break the ligaments, the wavelength of the liquid current to form a droplet. Basically, they just consider the surface tension is mainly the control effect, because surface tension of the liquid will maintain the minimal energy to make the droplet be spherical. And further, they have some modification on that. If you consider the viscosity Weber, later they find out you consider the viscosity of a liquid. That means that you will try to think about the surface force on the liquid ligament. Then they have some corrections on the formula. You need to consider nu L. Nu L represent the liquid viscosity. You will find out the length, the relation between the wavelength and the initial diameter of a jet. We modify by this term, but this term is under the square root. Okay, that means if you increase, if you have a more viscous liquid, then you will find out the wavelength actually related to the dj become a smaller. Okay, if this is a smaller, you can see they will produce the smaller droplet. Okay, which means that the viscosity give you some influence on the formation of the droplet size based on the original wavelength of a liquid current. And there is some importance mentioned here. In general, in more general case, drag force tend to tear the surface of the turbulent liquid jet into fine ligaments. That means the original dj becomes smaller. Okay, and the wavelength lambda becomes smaller. Then the droplet size predicted by radii, actually there is the maximum value. Okay, the upper limit, because the radii predicts the droplet size based on the ideal condition. They just consider the surface tensions will form the droplet size. But originally, the jet size, the diameter is remain the same as the initial droplet jet jet diameter. If you consider the direct force acting on the liquid jet and also the viscosity, most of them will give you the thinner jet, thinner diameter, thinner jet. The jet and the size becomes smaller, then the droplet size will be smaller. Then here you can conclude that the radii prediction, basically they predict the upper limit of possible size. Okay, this is a very good, very nice theory used to estimate how much, how is the diameter we may have by those kinds of disturbance influence. And there is another thinking about the sheet breakup. That means that if you increase the size of jet, as we described earlier, you need to consider the velocity difference, the velocity distribution along a cross section of the larger liquid jet. Now you will think about all of the breakup process will go through from the sheet breakup. I mean the liquid sheet and the liquid ligament, and then the droplets. Unfortunately, we do not have a proper theoretical predictions on sheet breakup. We just can give you some descriptions, especially on the physical appearance for the different kinds of breakup mechanism for for large size of the jet, of the liquid jet. Okay, I use the photos pictures to give you the understanding. They say the first category you may have, we say there is the so-called the ring disintegration. Ring disintegration, basically they tell you the whole spray catalyst basically is a spray surface, and the force created by surface tension will only cause there is some ligament occurs on the edge of the liquid sheet. Okay, then those kinds of free edge of a liquid sheet will contract into a thick ring. You can see there is some ring coming out, that just like a ligament, right? One by one, one by one, one by one. Then later on, they will break up to the droplet. Okay, this is the situation velocity. In this case, actually, the viscosity of the sheet is relatively small. It's 58 feet per second for these pictures. Okay, now it means that there is the under low injection velocity of the liquid. Here there is the kerosene and the water is a mixtures. Okay, and they control their viscosity as 15 centipoise. Okay, now if you increase their velocities, okay, you will find out there is strong interaction between the liquid sheet with the outer surroundings. Then you can figure out there is the second category for the breakup phenomena. We call this as a so-called perforated sheet. You can see there is some hole occurs in the downstream of the liquid sheet. All right, there is the hole occurring. Holes appear in the sheet at a certain distance away from the injectors, and growth rapidly in size. They become bigger and bigger until the ring, when the rings of the holes they meet together, and they will break into the ligament, and then those ligaments later on they will start to break up to droplets. Okay, now you increase the velocity furthermore to the 120 feet per second. Then you can see, as we described earlier, you can see the wave motion on the liquid sheet, and those kinds of wave disturbance will cut, will break the liquid sheet as the ligament. Then later on, the ligament will break into the droplet. As this is the typical features we already explained before. Finally, they tell you if you increase to the extreme velocity, so 350 feet per second, they tell you they have just kinds of air resections disintegration. That means that you do not, as we described earlier, when you increase the injection jet, the liquid sheet, the length of liquid sheet will become smaller, 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 smaller. Then maybe this completely disappear. The spray is just atomized in the vicinity of the injectors. Okay, this is a so-called. This is the final pictures you can understand. Okay. For the sheet atomizations or breakup, we do not have a proper theoretical predictions on it, but we just can give you some quantitative description on the physical features for the sheet breakup. Okay, now we shift to certain measurements on different kinds of spray characteristics used for identification on the application of a spray combustion. Okay, now first one, how to categorize the spray behavior. Actually, the droplet size is the most important one you need to consider. But mainly, how to describe your droplet size in your spray is the main issue you need to consider. The first one, usually for the spray combustion, we consider the droplets inside of the spray region. We treat it as a spherical shape. Okay, how can we have this kinds of spherical droplet assumption based on two criterion? Here I list as here. The first one, the droplet collisions, agglomeration, and micro-exploding effects are small. Okay, usually when you're dealing with the spray behavior, as we described earlier for the shift disintegration, if you increase your injection velocity very large, then you just have atomization occur in the vicinity of an injector. That means that when you have a jet impinging out, they have a very strong aerodynamic interactions. They will immediately break up so many tiny droplets. Okay, and this moment, when you think about a droplet already exists, so many droplets exist in the regions, then you try to identify the individual features for a single droplet. If they do not have collision, when you have a very so many droplets mixed in a small volume, then the droplet can have a big chance to meet together. That means that they will collide, agglomerate, or maybe, as I explained earlier, there is some a micro component droplet will experience those kinds of micro exploding process. Then in the process, the droplet size always changes. In the breakup process, the droplet size cannot retain the spherical. By consider those kinds of influence, if they are small, then we will think about droplet size will be spherical. And those kinds of assumption is applicable for the regions with the less dense spray. That means the spray is dilute. Usually, when you move away from the injection point a little bit, then the whole region in your spray field, actually the droplet exists is relative as a large distance. They do not have very serious collisions or agglomeration, and then we can say this spray is dilute. Dilute means in the total spray volume, you do not have too much liquid inside of it. Okay, and those kinds of liquid basically represented by so many tiny droplets, right? And since the total volume of the droplet size, the droplets is small, then they can well distribute in a large spray volume. Spray volume means including the liquid phase and the gas phase together. Okay, this is a spray. Okay, you follow. You sketch the spray cone. Then this whole cone, where we call this the spray field, spray region. And inside of spray region, you have a gas phase, maybe air or some vapor, and but for the liquid phase, then you have so many tiny droplets. Okay, then you bring the total volume of liquids, the droplet, compare with the spray volume. Then if this value is small, then we call this as a dilute spray. Definitely, you believe when you move away from the tip of the injectors to the far downstreams, you have more air coming in to entrainment to mix with water, to mix with the droplets. Then in this region, you can deal it as a dilute spray. Is a complete okay, but when you move closer to the tip of injector, now dilute spray assumption is not a good one, because there is just have a small cone volume, right? Small spray field, but in that regions you have so many liquid droplet in, almost occupies the whole region of spray. At that region, you cannot say it is the dilute spray. It should be the dense spray. The thinking will be different. You need to understand the variation of the spray characteristic from the injector port to the downstream side. Later on, we will describe the flame behavior. Basically, spray flame behavior is governed pretty much by those kinds of dilute or dense spray situation. This is the first criterion. You can treat the droplet as a spherical as the spray is under a dilute spray conditions. The next one, the wave number is low. Now, why we need to bring the wave number to this assumption? The wave number definition for wave number is equal to dynamic force divided by the surface tension force. This two force basically have an opposite effect. As I mentioned, the surface tension of your liquid try to maintain your droplet be more spherical to maintain the minimal surface energy. Okay, and this force, surface tension, try to retain the spherical shape. But dynamic force between the liquid, the droplet with the gas, that means that we are talking about a shear force acting on the droplet surface, and this shear force try to tear. Try to move your liquid surface to different shape. Okay, then the dynamic force actually they try to distort the spherical shape. But by comparing these two forces, if wave number is low, it's much smaller than 10. Much smaller than 10 means the surface tension is 10 times of dynamics force, then the surface tension can retain the spherical shape of it for your droplet. Okay, and this is the other assumption. And basically, the wave number usually is quite low for the general liquid fuel we use. And please remember here, wave number can be described by the density of the gas times the velocity difference between the particle, your droplet and the gas, okay, square. And here in the denominator, there is the surface tension divided by D, then you will have a non-dimensional wave number. You should remember the definition for wave number. But the meaning, the physical meaning for wave number is the dynamic force divided by surface tension force. For the case of wave number much smaller than 10, then you can assume spherical droplet assumption. You can have this assumption, okay? And both criterion A and B basically is easier to be found and to be justified in usual general spray burning conditions. Then you can have a confidence to think about the droplet will be spherical in our spray burning field. Okay, now you understand you can treat the droplet as a spherical. Now we try to think about if this droplet is spherical, now how to characterize its size. Okay, mainly you think about when you have a spray atomizations, and you try to make a control volume to think about the droplet size distribution in this control volume. Definitely you will not have a simple idea about all the droplet size are the same, right? It is impossible. Actually, the droplet size distribution basically controlled by the normal distributions. You can do so many kinds of different measurements. You always have this kinds of plot. Okay, show here. How to read this plot, and the horizontal axis represent the droplet size you may have. You do the measurement for different kinds of droplet size. Okay, and this droplet size distribution may be from the 0 to 200 or 300 micron. And the horizontal axis represents how much droplet number we have for different kinds of droplet size. Okay, if you go back to the very the earlier age, people try to measure the droplet size using the typical. I give you the example. They will use a plate, okay, or glasses. Then they will coat certain maybe H on it, or maybe coat some carbon on it. Then the whole plate will become brick, right? And you have a spray, and people will try to shift this plate very fast and move close into the spray field. When you have when you move this plate into the spray region and move very fast, that means you will have some droplets impinge on the plate, right? In a short time. If you move this plate is very fast, then the contact the time for the droplet on the glass is short. Then when you move this plate to the other to out of the spray, then you will see there's so many points, and those can show you the impact of different size of droplets. Then people will use because originally this is a plate coating by the soot, the brake soot, or some kinds of the carbon on it. Then the droplet on impinging on it, you will have a different kinds of point, maybe the empty point or weight point. Then you measure the size of the ink, the different dots. Okay, and here they tell you originally people will think, for example, there is the column shape, right? I give you some reading because, for example, for this one, they tell you the droplet size may be between here maybe 45 to 55, because when you do the measurement by using those kinds of coating effect, you can measure because they do not have the precise for individual droplet size, maybe 51, 52, 53. They just give you a range. Okay, then people will count the range, for example, 45 to 55. In this region, the average number, okay, you can mark your measurement on here. Then you can read like this. Here they say data D means the range of your droplet size you measure from 45 to 55, and how many droplets you have in this range. Then this is data N. Okay, which means the denominator here represents the how many droplet size you have, and the size between 45 to 55. Okay, and this number divided by total number. You when you do the all measurement, and then you can have so many droplets you count, and you find out the total number. Then this data N will tell you the how much percent for droplet size between 45 to 55. Okay, this is coming from the idea about the classical measurement on droplet size. Then you will have those kinds of column shape. Okay, but for the modern measurement, especially when you use the laser light optical methods, then you can actually precisely to measure 45 the number of 45 micrometer droplets, and 46, 47, 48, one by one. Then you can have a so-called continuous curve, okay, instead of those kinds of column representation. Okay, and here for both column shape distribution of the continuous curve, they give you the idea. That means the so-called distribution function. What's the meaning of distribution function? Distribution function give you the droplet size distributions for the different droplet size. Okay, when you read the number of your droplet by using the continuous curve, they tell you, for example, here for the droplet size equal to 120 micron, the value for the droplets with this size, they count it around very close to the 3.5%. Okay, and if you try to think about 100 microns, then your risk rate is just have a 6%. Okay, and those kinds of data can be calculated or counted from your measurement systems. Okay, and then they give you the distribution function. Those distribution functions give you the idea about the spread atomization. Actually, those kinds of distribution of droplet size, they will distribute in a large the diameter range. Okay, and when you extend to a large, that means the droplet size vary in different kinds of diameter. But if you have a narrow, okay, narrow, for example, this distribution function become narrow like a unit step function. That means that you will have a more uniform size spray. Okay, in that region, the droplet size almost the same. Okay, now the distribution give you the idea about the droplet size distribution you may have in this control body. Okay, here they tell you delta n divided by delta d basically is described by the column shape. But in modern measurement, actually the variation of the droplet size can be nano to maybe smaller than 1 micron. Then you will change the delta n divided by delta d by dn dd. Okay, and this tells you this is a so-called distribution function f of d. dn dd is equal to f of d. Okay, now the second point, people usually try to do the calculations by integrations. You can do the integration by using the f of d. F of d here, this is the distribution function. Then you do the integration based on d, dd. That means that when you, this is a number, right? Distribution to represent a number of your droplets under certain size. Then you times d, then you will do the integration. They will give you the cumulative number curve, and can be plotted by this way. This is a number, okay, because you do the integration from the around maybe 15 microns, because usually you may not have a droplet size smaller than 15th in this measurement. Sometimes you do have, okay, but here they tell you when you do the integration for the on the distribution function, you can count the accumulate number of the droplet size. For example, here at this point is 80, right? 80 micron. When you read this point, they tell you the droplet size less than 18 microns will be around 70%. Okay, that means that you look at the distribution function, you will find out there is a large portions of your droplet size less than 80. Okay, now when you read this data from the cumulative number curve, then you can have this kind of reading. And you move to the 120 microns, then you will have higher cumulative number ratio. Okay, then you can read through here around 85%. That means the droplet size less than 120 micron contains 80% of the total droplets. Okay. Now people try to, because the number is the one factor to think about that. But people think about the spread means, I mean the total volume you may have, the total surface you may have. Then they do different kinds of integration to see the cumulative volume or surface curve. Okay, that means that if you use the f of d is the distribution function, but you times, for example, you times the d cubic. That means that you count the total volume, then you will have the accumulate volume curve by this way. Then they read here, for example, 140 micron. They tell you the droplet size under 140 micron, their volume will contains the total volume of spray as 62%. Okay. Okay, now if you try to evaluate the volume, the total volume of the droplet size less than 100 in the total spray, then you can use this to find out how much of that. Okay, now you can see there is 60% compared with the number, the cumulative number curve represent different kinds of physical meanings you need to figure out. By this kinds of definition of integration, then they will bring you to have a different kinds of average method to estimate the droplet size. The droplet size, the mean diameter, for example, you do the automatic mean droplet diameters. In this example, they show you 76.61 micron, right? How to do that? Actually, they just calculate the total diameter, okay, times the number, then that divide total number, then they will have an average arithmetic mean value, the average diameter, then that represent the 76.61 micron. But if you calculate the number with the volume, then you will have a different value. Later on, we will introduce the so-called solid mean diameter, and probably refer to our spray combustion. Then they will give you the different number, 109.2 micron, and the value are completely different. 67 6.61 micron represents the average diameter characteristic. But so mean diameter will give you the other idea to bring the total volume you may have compared with total surface for the spray. Then they will give you the idea to describe spray burning. I will discuss with you later in next video.